Hey there, and welcome to This Explainer. Today, we're going to do something really fun. We're taking the seemingly intimidating high-level physics of thermodynamics and shrinking them down so they fit right on your kitchen stove. If you're a high school science student, or honestly, just someone who wants to understand the physics of the world around you without getting completely bogged down in confusing jargon, you are in the exact right place. We're going to use a simple kitchen pot to master the fundamental principles of thermodynamic systems. We've got a lot of ground to cover today. We'll start with the anatomy of a system, break down the rules of exchange, look at 3 specific types of systems, define what a state is, and then wrap it all up with a quick practice round. Let's dive right in. First up, the anatomy of a system, or what I like to call the geography of thermodynamics. Because in physics, before you can measure anything, you really have to know exactly where you're looking. So, what actually is a system? Officially, our source defines it as a region of space containing a quantity of matter whose behavior is being investigated. But let's simplify that. Imagine you're boiling water for a big, chaotic pot of pasta. The actual water inside that pot, that is our system. It's the specific stuff, the matter, we want to look at. We don't care about the chef, we don't care about the recipe, we only care about that specific quantity of water. Now, notice how the physical setup naturally defines our terms here. A boundary is simply what separates a system from a surrounding. In our kitchen analogy, it's literally the metal walls in the bottom of the pot. It is the physical line drawn right between the water we're studying and, well, the rest of the world. And that brings us to the surrounding. The source material defines this as literally anything outside a system. It's really that simple. Everything outside those metal walls, the air in your kitchen, the hot stove burner underneath, the countertop, even you standing there waiting for the water to boil, all of that makes up the surrounding. Now, if we take our pot of water, the system, and combine it with the entire kitchen surrounding it, we get what thermodynamics grandly calls the universe. I know, it sounds like some massive cosmic sci-fi term, but in physics, it just means the totality of what you're studying, plus everything outside of it that could possibly interact with it. System plus surrounding equals universe. Moving on to section 2, rules of exchange. Basically, we need to know what's allowed to cross that boundary. See, things don't just sit perfectly still, they interact. And our system only allows 2 specific types of things to cross its boundary to interact with the surroundings. First, we've got energy exchange interactions. This includes stuff like heat, work, friction, or radiation. In our kitchen, this is the literal heat from the stove burner pushing right through that metal boundary and warming up the water. Second, we have matter exchange interactions. This is the actual physical motion of molecules crossing the boundaries. So think of the water turning into steam and floating away into the kitchen air. Heat is the energy crossing the boundary, and steam is the matter crossing the boundary. Make sense? Okay, section 3, 3 types of systems. This is where we get to play with our pot analogy and see how modifying the setup creates distinctly different systems, all based entirely on those rules of exchange. First up is the open system. Our source defines this as a system where both energy and mass, or matter, interactions take place. Think of this as your standard pot of boiling water with no lid. If you leave that lid entirely off, you create an open system. Heat energy enters from the stove, and physical mass, that steam, freely escapes into the air. Both energy and matter are totally on the move here. Next, we have the closed system. Here, only energy interaction takes place. Imagine you snap a heavy, tightly locked lid onto that pot. Boom, you've got a closed system. The heat energy from the stove is still getting in through the metal boundary, making the water hotter and hotter. But because that lid is locked tight, the mass, the actual physical water molecules, is completely trapped. Energy crosses, but matter doesn't. And that brilliantly illustrates our third type, the isolated system. By definition, this is a system where absolutely zero interaction takes place. Imagine taking your pot off the stove and pouring that water into a theoretically perfect vacuum-sealed thermos. Now, I know your actual thermos probably lets your coffee get cold by like 3 p.m., but in physics, a perfect isolated system means absolutely no heat energy escapes through those thick insulated walls, and no physical mass can get out either. No energy exchange, no mass exchange, it is completely isolated from its surroundings. To keep all this straight, we can just use a simple grid to categorize our setups. It perfectly visualizes these interactions. Look at the open system. It says yes to energy exchange and yes to mass exchange. The closed system says yes to energy, but no to mass. And the isolated system? It shuts the door completely. No to energy and no to mass. Honestly, if you can just picture this grid in your head, you've already mastered a massive chunk of high school thermodynamics. Let's keep moving. Section 4. Defining the state, or taking a snapshot in time. Let's pause the boiling action for a second. This source material tells us that the state of a system is simply its condition as described by certain properties. Think of it exactly like taking a photograph. When you snap that picture right at that exact snapshot in time, everything freezes. At a given state, all the properties of the system, stuff like its temperature, its pressure, its volume, they're completely fixed. They have a specific unmoving value. The second you put that pot back on the heat and the temperature ticks up even a little bit, you're moving right into a brand new state. All right, section 5. Time for a little practice. You've learned the definitions, you've got the kitchen analogies down, so let's put your new knowledge to the test. I'm going to give you a scenario, and I want you to mentally categorize it before I reveal the answer. Ready? Here's the first one. You've got a boiling pot of soup on a hot stove, and the lid is completely off. What kind of system allows both heat from the stove to enter and steam in the air to move across the boundary? If you guessed open system, you hit the nail on the head. Because the lid is off, the physical steam, which is matter, is escaping. And because it's sitting on a hot stove, energy is transferring. Both energy and mass are interacting with the surroundings. Awesome job! Okay, let's try another one. Picture a tightly sealed pressure cooker sitting on a hot stove. Heat is pumping right into the metal, but absolutely zero steam is allowed to leak out into the kitchen. What do we call this one? That is a closed system. The locked boundary of the pressure cooker completely traps the physical mass, leaving only the heat energy from the stove to exchange across the boundary. You've locked the matter inside, but you haven't blocked the energy. All right, last one. What if we take that piping hot soup and pour it into our theoretically perfect thermos, the one that perfectly insulates the temperature and seals the liquid away from the rest of the kitchen so absolutely nothing escapes? What kind of system is this? You guessed it, that's an isolated system. Absolutely no interactions of energy or mass are taking place here. The surroundings have zero effect on what's locked inside that perfect thermos. To wrap up this explainer, I want to leave you with a massive, kind of mind-bending question to chew on. Earlier, we defined the universe as the system plus the surrounding. Basically, it encompasses literally everything that exists. So based on our own definitions, if there is no outside for the universe to interact with, does that make the entire universe the ultimate isolated system? I mean, think about it. Can any mass or energy possibly escape a boundary that literally contains everything? Thanks so much for joining me on this explainer today, and keep looking for the physics hidden right there in your everyday life.